All right, everyone, let's start solving the NEET 2025 paper. And we are actually starting with the most difficult question that was asked for the NEET 2025. And what is this question? Let's jump in and see. What is it? We have a water tank, right? It has one wall at x equal to L and can be taken to be very wide in the z direction, right? When filled with a liquid of surface tension S and density rho, the liquid surface makes angle theta naught, which is very much less than 1, right? With the x-axis at x equal to L. If y of x is the height of the surface, then what is the equation for y of x is the question. And there are certain approximations that you can actually use in this, and the options are given. So how to solve this question? Which chapter it is? It is nothing but mechanical properties of fluids only, right? And what concept are we going to apply in that? The case of surface tension. Very simple case. Okay, let's see how actually we can solve this. Before that, let's make a clear picture of this. Okay, what is this actually? Okay, how is this tank and how is the water there in this? Let's make a clear understanding of this. So for that, I'm trying to draw actually this diagram here. Okay, so let's see here. The it's very clear. We have a tank we are seeing, and this is how the question is coming. Okay, or the water tank, how the water it is in. This is how they are meaning actually. Okay, so let's say this is our tank, and the liquid surface will be like this. Are you getting that? So towards the wall, if we are seeing, which is at x equal to L, right? So it will be gradually climbing up, okay? And from there, if you come towards the left, okay? If you continuously go, what is that you will be seeing? The curvature actually decreases, 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 decreases like that, right? So at x equal to 0, if you are seeing, is it a wall? No, it is not a wall. It's not given like that in the question. So let's assume this will continue. There is no wall actually towards the left of it. This will continue. How long it will continue? Let's say toward to infinity, the height of the liquid actually becomes 0, where at infinity it will become, let's take it like that. So that is what the basic of this question. Okay, now how actually to solve this question? We are going to apply surface tension directly to this. Okay, and now we also know the concept of pressure difference. If suppose you have a liquid meniscus, we know that the pressure above and below it, if it is a curved liquid meniscus, the pressure above and below will be different, correct? And that pressure difference, we are going to directly connect it with the curvature of this, and that's what we are going to do it in this question. Okay, so let's understand, or let's find it out how to find that pressure difference first. Okay, so for that, let's consider here a liquid meniscus, for example, where the curvature is continuously changing. So let's consider these 2 points, let's say A and B. We are considering this liquid is in equilibrium also. Okay, so if you consider these 2 points, A and B, let's say they are at the same horizontal level. My question it is the pressure at these 2 points be same or different? The simplest answer for this is the pressure at these 2 points be same. Now, how is this possible? See here, above the point B, we have a Y length of liquid, but above A, we don't have. But still, why is this pressure difference or the pressure at these 2 points? How can it be same? The simplest answer to that is lying on the curvature at these 2 points. We say curvature at A, let's say it is A, KA, and this point C, which is directly above the point B, let's say it is KC. Okay, the curvature at A will be less than the curvature at C, obviously. Okay, so because of that, you can tell the pressure difference above and below the point A, right, taking is delta PA, and that will be less than what? Delta PC, obviously, where delta PC is the pressure difference between the point above and below the point C, if you are seeing just above and below the liquid surface, if you are seeing. Okay, and this pressure difference delta P, let's say delta PC minus delta PA, this will be basically equal to what you can write, Y rho G, you can write. That is this pressure difference that is having between these 2 points that you are seeing, that pressure difference is balanced by what? The Y length of the liquid column there. Okay, so but again, one more point, if you are thinking of it this way, if this point A that I have taken, if it is toward the left continuously, as like in the given problem, okay, let's say it is at that infinite point. At that infinity, what will be that curvature that will be coming? If it is continuing, if the curvature is 0, okay, at point A, if I'm taking the curvature is 0, then pressure difference at A will be equal to what? Zero, you can tell. Essentially, that surface is flat. So the pressure difference above and below will be zero. That like that we can actually take. Okay, so we will be taking like what? Delta PC. What will that be equal to? Y rho G. We can actually easily take it like this. Did you understand this? Now, coming back to our problem once again. Okay, see, in one more way, I'm going to write this pressure difference. How do we write this? See here in the same, like in the case of in this problem, what is it? The tank that we are seeing, right? We have the tank once again, the liquid, how it is. The liquid is like this. Okay, this is continuing up till infinity. The y length we are seeing. This is the x-axis I'm taking. This is the y-axis, and this is the z-axis. So here we have pressure difference in one more way I can write. And how do I write that? Delta P. We know this relation very clearly. How do I relate it with the surface tension? If delta P is equal to S into 1 by R1 plus 1 by R2. This is a known relation for us. Correct. See here, what will be R1? R1, you can write it as what? Rx. And what is that equal to? R, we can write it. And what is R2 equal to? R2 is nothing but Rz, right? See, Rx is actually the radius of curvature of that surface that you're considering with respect to the x plane. And this is along z plane that we'll be taking. And this you can take. Since along the z axis, it is essentially wide, we can take this as what? Infinity. There is no curvature coming along what? The z plane. Basically it is essentially flat along the z axis, so I'll take it as what? Radius is actually infinity in that case. So here the pressure difference actually become what? S into 1 by R plus 1 by infinity, it will be becoming, right? And that you can write it as what? S by R, we can actually write. I hope that is clear. So at this point, what we are going to do, I'm going to connect this radius with the curvature. Okay, now how I'm going to do that? Let's consider here two spheres. Okay, let's say one is small, one is big. Let's say this radius is R1, this radius is R2. Okay, I've taken R1 is less than R2. Obviously, very clearly we can see that the curvature, how then it will be related? The curvature of the smaller sphere will be more than that of the bigger one. Very clear. Correct. So here you can see here one very easy relation between the curvature and the radius. What is that? Curvature is inversely proportional to what? Radius. Okay. If you know this proportionality only, you can do this problem. But the actual relation, it is very easy. It is actually nothing but curvature is nothing but 1 by r only. That is the easiest thing. One more thing I need to note here. See, if I'm going to write how the curvature, I mean the slope, okay, the slope of the liquid meniscus. If you see here, for example, this is that liquid meniscus. The slope is continuously changing, correct? It is increasing from left to right if I'm going. This is along the x-axis and this is along the y-axis if I'm taking. If I move from left to right, correct? If I move from left to right, what is that we are seeing? The curvature is continuously increasing, like that we understand. Okay, now how do I relate with the curvature? That one, that's what we are going to see here. And that is a very simple relation. Okay, how the slope change with the distance? At what rate the slope change with the distance? That is what the essentially what curvature on. So you can write curvature is proportional to what? D by dx of slope is nothing but what? Y dash. Y dash is nothing but what? First derivative of y with respect to what? X. Okay, so you can write k proportional to d by dx of y dash, or k proportional to what you can write? Y double dash. Easy relation. If you know this much only, we can do this problem. Or I'll tell you for keeping this in mind, the curvature, how is it related to y double dash? Direct relation also I'll tell you. What is that? K is equal to y double dash divided by 1 plus y dash square whole to the power 3 by 2. In that, if you are taking the slope, y dash is small. If you are taking, if you take y dash is small, what you can do? K approximately equal to y double dash, easily you can take. You get in that. So what will happen to our relation here? We have delta P. What is that equal to? S by R relation that we are having. So how you can write this relation now? Delta P is equal to S by R. Correct? And that you can write it as equal to what? S by R is what? S into K you can write. Now what is K is equal to? We have already got K is equal to Y double dash, or that is equal to what? D square Y divided by dx square you can write very easily. So you can write this equation as what? S into d square y divided by dx square, you can write like this. Now I'll relate it back to this again. Delta P is equal to y rho g back again. Okay, so here our problem is now very easy. Like this, we have brought this up to, we have x equal to L. At x equal to L, we are having the wall. Okay, and the liquid surface is going like this. I told you already the liquid, this is not wall. At x equal to 0, it's not the wall. This is continuing up till infinity. The height actually y becomes 0. Okay, at this point. So at this point, wherever point, at whatever point actually we are seeing now, we are trying to relate the pressure difference with the curvature. You can write this simple relation. What is that? Delta P. In two ways we have found now. No. What is that? Delta P is equal to S into d square y divided by dx square. That is equal to what? Y rho g we can write. Or the final relation, very easily we can write. What is that? D square y divided by dx square. And what is that equal to? That is equal to rho g by s into y. And that is our result here, where you can see option number 2, which is d square y by dx square, that is equal to rho g by s into y. This is the solution for this. Okay, it is a bit lengthy, but we have done this routing on the concept. Okay, and just some mathematical formulations we are using in this. I hope that is clear to you all.